The speed of light is the highest measurable speed. Does not mean the fastest a ship can travel to which it is referred with in physics. Space is a vacuum unlike Earth's gravity, which is measurable. Space has no gravity. It is these two quantities the speed of light speed limit is referred by. If the vacuum has no gravity, which slows moving masses when moving through, the speed limit changes. Why? Because no gravity. Relativity also refers the vacuum of space, the vacuum, to be made of the same quality as Earth's filled gravity field. This also is measurable and in the same way. In space, light speed source is conserved, meaning it doesn't stop there. Further acceleration can convey by Newtonian mechanics and dual acceleration theory. The reason for thus is empty vacuum. Silpstream, faster than light speed corridors, become reality at the most deepest depths of empty vacuum. Because no resistance. Gravity acts as resistance to moving objects moving through space. Veli changes include resistance gravity fields. In space where resistance is zero, or almost. More energy propulsion can be implied. These are the foundation mechanics on the quantum physics theory that will replace relativity. Rodney Kowecki.
You know, there aren't defined space vacuum layers in the same way that Earth has atmospheric layers, like the troposphere or stratosphere. Instead, outer space is generally described as an extremely high-quality vacuum. As you move farther from a planetary body, the particle density and pressure gradually decrease. It's fascinating how the vacuum quality varies significantly depending on the region of space. Scientists classify vacuum levels based on pressure ranges, often measured in torr, which is a unit of pressure. So here's a breakdown of how different regions of space relate to these vacuum classifications. It's really intriguing how these classifications help us understand the vastness of space. Let's define a vacuum. A vacuum is a space devoid of matter. Now, outer space is considered a near-perfect vacuum because, well, it's not truly empty. It still contains trace amounts of atoms, molecules, electromagnetic radiation, cosmic rays, and even mysterious components like dark matter and dark energy. Isn't that just mind-blowing? The transition to space is gradual. The density of matter and thus the level of vacuum doesn't change abruptly. The exosphere, which is the outermost layer of Earth's atmosphere, gradually thins out and fades into the vacuum of space with no clear boundary. Oh, and the traditional boundary of space, known as the Kármán line, is set at an arbitrary 100 kilometers altitude. It's amazing how we define these boundaries, isn't it? So, a perfect vacuum, also known as zero torr, is really just a theoretical ideal. It's defined as a space completely devoid of all matter, but honestly, such a place isn't known to exist anywhere, not even in the vast stretches of deep intergalactic space. The video below, by the way, describes how a vacuum is actually created here on Earth to simulate the conditions of space for testing equipment. Solar 60, creating a vacuum to simulate space, focuses on how we create a vacuum here on Earth to mimic the environment of space. This process really highlights just how high the vacuum level is out there. Now, there aren't defined space vacuum layers like we have atmospheric layers on Earth, such as the troposphere or the stratosphere. Instead, outer space is generally described as an extremely high-quality vacuum, where the particle density and pressure just keep decreasing the farther you move from a planetary body. And honestly, the vacuum quality varies quite a lot depending on the region of space. Scientists actually classify vacuum levels based on pressure ranges, and these are often measured in torr, which is a unit of pressure. So here's a breakdown of how different regions of space relate to these vacuum classifications. So let's talk about what a vacuum really is. a vacuum is a space devoid of matter. But you know, outer space is actually a near-perfect vacuum because it's not truly empty. It still contains trace amounts of atoms, molecules, electromagnetic radiation, cosmic rays, and even mysterious components like dark matter and dark energy. Now, the transition from our atmosphere to space isn't sudden. The density of matter and therefore the level of vacuum doesn't change abruptly. The exosphere, which is the outermost layer of Earth's atmosphere, gradually thins out and just kind of fades into the vacuum of space with no clear boundary at all. The traditional boundary of space, known as the Kármán line, is actually set at an arbitrary 100-kilometer altitude. When we talk about a perfect vacuum, zero torr, that's really just a theoretical ideal. It means a space completely devoid of all matter, which, as far as we know, doesn't exist anywhere, not even in deep intergalactic space. And by the way, the video below describes how a vacuum is created on Earth to simulate the conditions of space for testing equipment. Solar 60, creating a vacuum to simulate space, focuses on, well, creating a vacuum right here on Earth to simulate space. This really highlights just how high the vacuum level is in the space environment. We look at Spacefield layers in much the same way we view the ripples in Earth's seas. Gravitation acts on the ocean as it spins. Darius C. illustrates a view of space as a field of empty vacuum that, when it rotates, this motion creates ripples in the fabric of the spacefield, and celestial matter exists inside. The universe is in motion. It is not settled, but rather caught in a kind of cosmic speed limit, with the existence of Newtonian energy creating a gravitational realm between the celestial bodies. Now, the universe expands. This expansion creates motion. Gravity is formed between the static and the separation of the planets by Casimir separation. This creates corridor passages between the celestial bodies that allow for superluminal travel. There exists no speed limit, yet the velocity propulsion transforms into a cosmic energy propulsion mechanics. Energy is conserved and isn't stopped. With a greater propulsion mechanics in engine design, corridor passages are there to lead our space travelers through and beyond light speed. Energy is a definite truth. Spacefield layers are a fact of the truth, where all matter is defined, existing in its creation made of layers, so is the space field. Einstein defined this in his light speed theory, illustrating that light velocity is layered by seconds on the clock. You know, each second defines a new light speed velocity. But light, well, it's a diminishing element that's not physically attainable to anything but its own molecules. The space field, it's quite fascinating, really. It's a physically attached element that controls the surrounding matter. It's like it manages the orbit or rotation of the celestials, you see. It retains this zero vacuum carrier platform that holds nothing back. And here's the thing, it holds a physically implied position to the bodies in motion within it. It exists in a physical form, within which all celestial bodies exist. Isn't that just intriguing? It is the space field body that shrinks with the change of acceleration. If space was absolute, there would exist no change in speed and acceleration. Space travel and time would be absolute. But because the space field grows or expands, the universe can be warped, shrink, and change with the existence of the celestial bodies and objects in motion. As a physical body, space is layered into measurable layers based on Hubble mechanics and the rate of expanse. These layers exist and are measurable, not only by the Hubble rate, but also relative to the rate on time, seconds on the click. A travelocity to a far-off star can be arrived to in seconds, relative to the hands on a clock, sooner by advancing the speed. But in quantum physics theory, Einstein's famous equation is expandable and is not limited. There is no way in Einstein's speed limit that Casimir force forms space corridors in the universe.
E equals mc squared. Though relativity asserts Earth gravity as the manipulating force for mass increase due to acceleration, it lacks the performance to the lack of mass itself in Spacefield space travel. Quantum physics perspective shows that there is a subtraction element to E equals mc squared in space maneuvering while in space. The two elements involve the first Earth gravitation but also a subtraction clause to low-density fields, zero-point energy fields. Gravity, which is explained as manipulating energy, the moving mass doesn't explain a moving mass in the lack of gravity. The single E equals mc squared equation do not explain the full scenario. Big G, little g equations. The big G is based on the same suffix as the little g equation where in fact they don't. They are opposite scientific equivalence equations. It is this analogy that optimizes relativity into an unfinished work, as it is the hope that quantum physics theory perspective will join theoretical physics into better standard physics theory. While Albert Einstein is famously known for the mass-energy equivalence formula E equals mc squared, the concept of mass itself predates him. Isaac Newton, in his Principia, defined mass as the quantity of matter arising from density and bulk, distinguishing it from weight. Furthermore, the idea of mass-energy equivalence, though not in the exact form of E equals mc squared, was explored by others before Einstein, including Henri Poincaré and Olinto de Pretto. Here's a more detailed look. Newton's contribution. In 1686, Newton defined mass in his Principia as the measure of matter based on its density and bulk, and he clearly differentiated it from weight. Early explorations of mass-energy equivalence. Olinto de Pretto. In 1904, de Pretto published a paper suggesting that the potential energy of a moving particle could be expressed as mv squared, linking it to the mass of a particle vibrating at the speed of light. Henri Poincaré in 1900 also discussed the relationship between energy and mass, particularly in the context of electromagnetic phenomena, though not in the same concise E equals mc squared form. Friedrich Hasen-Orel. In 1904, Hasen-Orel derived an equation E equals 3/8 mc squared relating energy and mass, though his work is noted for some differences and potential oversights compared to Einstein's. Einstein's breakthrough. While others explored the relationship between mass and energy, Einstein's 1905 paper on special relativity provided a more complete and accurate understanding of the mass-energy equivalence, culminating in the famous E equals mc squared. He also demonstrated how this relationship is connected to the conservation of momentum and the behavior of systems emitting radiation. In essence, while Einstein's E equals mc squared is a cornerstone of modern physics, the concept of mass, and the early explorations of its relationship with energy, were developed by earlier scientists like Newton, Poincaré, and others, according to physics journals and physics forums.